Hello, everyone. I will present future planning in NLP. I'll start by introducing myself. In my former role, I have been with NICE System, led the NLP research group. We were the first company to deploy speech recognition, emotion detection, and text analytics solutions in call center, including healthcare. I'm now at Intel leading applied NLP research to increase adoption of deep learning in the industry and very active in state-of-the-art NLP research. Text classification is the process of understanding the meaning of the unstructured text and organizing it into predefined classes. For example, for classifying the topic of services request and routing the request to the relevant bot or agent. It can also be very useful, for example, for sentiment analysis, when you need to classify the textual input to 3 classes, positive, negative, and neutral. And it can be also useful for other classification tasks. According to Gradient Flow, 48% of large companies are using NLP for text classification. So this is one of the most popular NLP tasks in production. Let's see 2 examples in the healthcare domain. The first one is we need to label the following sentence based on whether it is related to an adverse drug effect, ADE. An adverse drug event is defined as harm experienced by a patient result of exposure to a medication. The second example, more challenging task, you need to label the following publication abstract based on whether it is related to one or many of HOC 10 cancer types. And HOC, the hallmark of cancer's corpus, benchmark consists of more than 1,500 PubMed abstracts, manually annotated at sentence level by experts with 10 currently known hallmark of cancers. So I'm going to start by talking a little bit about what is future planning, specifically for text classification and why it's important, and then continue to talk about how does SetFit, this is a method that we developed, is actually being applied for future planning, and also talk about the test case for achieving ecosystem adoption and applying few-shot in production. So let's start to talk about few-shot learning, more specifically few-shot learning with transformer models. Traditionally, when we want to fine-tune a transformer model for a specific task, for example, if it's topic classification, like in this image, where the task is to classify a document to 1 or 3 topics, we will need about a few thousands of labeled examples in order to reach acceptable accuracy. The need for so many labeled examples in order to fine-tune the model is a major obstacle for organization and companies because it's very time-consuming and costly to manually label those examples. And this prevents, of course, the deployment of NLP and AI in general in many companies. Few-shot learning is about training models using a small amount of labeled training data. There is no formal definition of how small the training data should be, but in practice in NLP, we are talking about 8 and to 64 samples. And currently, we see that few-shot learning draws a lot of attention, both from the research community and from the industry because of the high potential to break one of the major barriers of AI. Few-shot learning has been around for several years, but it was the release of GPT-3 by OpenAI that really made few-shot learning popular. The title of GPT-3 paper was Language Models Are Few-Shot Learners. And in GPT-3, the input to the model is a description of the task in natural language, followed by some examples that demonstrate what the task look like. And then finally, we ask the models to predict the output based on the instance. So in this specific example on the left side, we start by specifying a task. In this case, it was translate English to French. And then we give some examples and ask the model to translate cheese to French, and hopefully the model will generate the right answer. This particular type of future learning is called in-context learning, and that's because the model parameters are not adapted. There is no gradient update. It's purely an inference time prediction. The task description and training data are input as primary data at inference time. It was really exciting for the community to see for the first time that a model can learn from just a few examples without any parameter tuning. It brings up one step closer to the way a human would learn the task. The authors also showed that as you increase the size of the model, the performance increases. So if we look on the graph on the right, we can see different sizes of GPT-3 and the average accuracy across several NLP tasks. And we can see that rather as the model become larger in few shot regime, even with 400 million parameters, the average accuracy is around 30. Whereas when we scale this up to 175 billion, we are now looking at a scale close to 60. This is non-trivial gain, but of course, this gain comes with a cost. So the main two challenges of in-context learning is that first of all, we need to come up with a good task description and some good examples. And this usually is quite critical in terms of the performance. And it of course, depends on the choice of those prompts. The other practical challenge is that trying to actually deploy 170 billion is really quite hard in practice, and it's really very inefficient and costly. So although this is very promising, it has those two limitations. The most recent approach for future learning is based on parameter efficient fine-tuning. This is an idea that goes back a few years. Instead of fine-tuning all the parameters of a language model, what if we could find a way to fine-tune only a small number of the parameters? So in practice, we insert special layers, which are called adaptive layers. And then we essentially just train the weights of those adapters while leaving the rest of the network untouched. So the idea about adapter is widely used for increasing the generalization of models in a wide range of applications. And just recently, a method called TFU, which is based on adapters, was proposed for future learning and became the state of the art. And what the authors show in their paper is that TFU not just outperforms GPT-3, it is also far more efficient. So this is a great step forward, having both high quality models and also ones that are faster to train and inference. But again, TFU also depends on manual prompts engineering. And when we run our experiment as part of the SetFit paper, we found out that we had to spend a fair amount of time coming up with a clever prompt to adapt this kind of approach to neural data sets. And the other thing is that the performance depends on a large 11 billion parameter model. So although this is a great step forward, we still have some limitation here. So the question, can we do better? Mean that we maybe can, without any depending of very large generative models. And second, even no depending on manually crafted prompts, and of course, quite efficient. And the answer is yes, we can do that. Our paper proposes SetFit, which stands for Sentence Transformer Fine-Tuning. Sentence Transformer are pre-trained language models which are designed to generate an embedding vector that represent the sentences in their input. And the idea behind SetFit is remarkably simple. Essentially, it breaks up text classification into a two-stages training recipe that involves, first, adapting a pre-trained sentence transformer for few short text classification based on contrastive learning. And we will see it in more detail shortly. And second, then we use adapted sentence transformer to produce embeddings that are used as features to train a very simple classification head, even a logistic regression. I mentioned that we use contrastive learning to adapt the sentence transformer. And let me explain what is exactly contrastive learning. So since it is more intuitive, I will give an example from computer vision, which is where this idea originates. So the basic idea of contrastive learning is to adapt the network so that the resulting embeddings are pushed into regions of the feature space such that the images that are similar are clustered together, and images that are different from each other are pushed apart. So in this example that we see on the left side, we start off with an image of a golden retriever. This is typically called an anchor. And the idea is that this might be the class dog. And this other image here, and a tiger, is obviously a different animal. So we might have another class for tiger. So basically what we do is encode all these images together, and then we measure the distance between the embedding of a dog with an augmented version of itself, and also the distance of dog compared to the tiger. So finally, we use a loss function that progressively minimize the distance between the similar dog images and maximize the distance between dogs and other types of objects. This will help us to construct an embedding space with clearer classification boundaries between classes. So now the main question is how to integrate contrastive learning into the textual domain. In essence, this translates to the question, how do we generate these positive and negative pairs? In practice, we just select sentences from the same class as positive pairs and sentences from the different class as negative pairs. And once we have those pairs, we can fine-tune the transformers in a contrastive manner. As we can see on the 2D plot, after fine-tuning, the sentences belonging to the 2D different classes are separated, whereas before the fine-tuning, they were mixed together. So let's see some of the results of SetFit. We tested SetFit on 6 different data sets in a few short regime, using only 8 samples per class here on the top and 64 samples per class on the bottom. We compare it to the range of different state-of-the-art baseline, the standard fine-tuning approach, if using Roberta, for example, AdaPet, which is another method for few-shot learning, and TFU that I explained, which is a parameter-efficient training approach. So now when we compare the average accuracy across all the data sets, we can see that the SetFit consistently outperforms the standard fine-tuning, and also the AdaPet, and it's comparable to TFU despite being about 30 times smaller. We also compare the training and inference time of SetFit and TFU. For example, on the right, you can see that training TFU model on A100 GPU will cost roughly $0.7, which is 28 times more than 2.5 cents it costs to train SetFit on the same data set. And from Intel point of view, people can even run SetFit on their laptop CPU. It takes just a few minutes to train through these 8 labeled examples and 64 examples. In the previous slide, we saw results for datasets which were not specifically intended for future learning. Now we will see results on RAF benchmark, which is the de facto standard future benchmark for text classification. RAF was presented last year in Europe. It contains 11 diverse future tasks and provides only 50 labels for training, and it's a fully blind test. So we submitted two versions of SetFit. One was 100 million parameters, and the other was 350 million parameters. And we can see in the table, the smaller SetFit outperformed GPT-3 while being 1,600 times smaller and without using any prompt at all, which is a major advantage. Overall, it's clear that SetFit demonstrates the best parameter efficiency with relation to performance in comparison to any other models on the leaderboard. And here we see also Raft has been used by Stanford as part of their ELM benchmark. And we saw the data efficiency, and now we can see the model efficiency of SetFit. So the graph shows the Stanford comparison of foundation models. The x-axis is the model size in billions of parameters, and the y-axis is the average accuracy on the RAF benchmark, which is the standard future benchmark. We can see clearly that SetFit on the left side, the top left side, outperform the much larger models. For instance, it outperformed even models like more than 500 billion parameters like Megatron and GPT-3 and OPT with 175 billion. So even though SetFit is much more smaller and much more efficient, it actually gets quite high accuracy. The standard SetFit contains only 100 million parameters, which is basically the size of model like BERT. We also try to compare. We ask ourselves if you are trying to evaluate SetFit on medical data, on text specification medical data, and this specifically was on the HOC dataset, which is the multi-label benchmark for the hallmark of cancer. And we tried not the few shot, but the full shot training of the benchmark. And we compared the results to state-of-the-art models that was trained from scratch on bio and medical data. For example, models like BioBERT, PubMed BERT, and also BioGPT, which considered to be state-of-the-art for this specific task for multi-level classification. It's also considered to be state-of-the-art for Q&A in the medical domain. And what you can see here, quite surprising, that SetFit actually outperform models that was trained from scratch on bio data. It's even more efficient, so more than 3x smaller, and competitively with BioGPT, which considers state-of-the-art for this specific task. So it's quite promising results. So I showed the SetFit is comparable to other state-of-the-art fusion methods. In our main experiment, we used a version of SetFit that is based on MPNet, a sentence transformer that includes 100 million parameters. And the question we asked ourselves was whether SetFit can be used even in a much smaller and efficient model, and it can be useful for practical deployment. For this purpose, we tested SetFit in a distillation scenario, where the teacher model was SetFit that is based on MPNet, which is the 100 million parameters, and the student model was based on mini-LM, sentence transformer, that contained only 15 million parameters. So it's about 7 times smaller than the teacher, which is MPNet. So the first step of the distillation setup was to train the teacher model using 16 labels, example per class. And then, as you can see in the block diagram, we trained the student sentence transformer to mimic the teacher by minimizing the loss between the student output and the teacher cosine similarity. We have all the details in the paper. Next, we train the classification head of the student by using the embedding produced by the student and the logis produced by the teacher. Here are the kind of the results. So these tables show the comparison between SetFit MPNet and the SetFit student model, which is the distill model. Here, and we use the 16 sample per class. And what we see here, the score here is the average score across our data set. And we can see that our SetFit student fell short only in 2 points compared with the teacher model, but is even 6x times faster than the teacher. So the bottom line is that SetFit can be even more efficient when using smaller models in distillation setup. And of course, we can take it to production. And this slide also shows that we can do even more and even add quantization. So we start SetFit with MPNet, which is 100 million parameter, and it's of course about 440 megabytes. So and then we are applying distillation to get the mini LM, which is the 15 million size model, and then we also apply quantization using Intel CPU framework to get even a model that is 20 million bytes, which is actually 22x smaller than the one that we started with, which is the 440 million bytes. So it's additional more than 20x comparison to the teacher, and it also translates to 10 times faster on CPU without accuracy loss. So this work was a collaboration research between Hugging Face, Intel Lab, and UKP. We published a paper, a blog. You can have all the details here. And also the code is available with many examples, with many notebooks examples that you can follow. Just a few words about the impact of this work. SetFit make a lot of impact on the research and development community. We have right now we have more than 1,200 GitHub stars, and in the last 4 months we had more than 150,000 installed, and multiple blog posts, YouTube videos reviewing the SetFit paper. And our goal is to make SetFit applicable for any text classification task. If you want to go to production, you want to get much more smaller models and efficient, SetFit is actually the best method to do it. But this is my last slide just to recap. So we offer SetFit. This is available in our GitHub repository. This is really fast compared and of course smaller compared to the larger model like GPT-3. If you compare it with distillation, it even can get to 20K speed up related to the larger model. It can take a few minutes to train on a CPU, and it's today also available with service providers, NLP service providers that offer this as a service with additional, for example, active learning capabilities like Argila, Mantis, and Wiki.force. So thank you very much for listening, and I hope you can get into our repository and start using SetFit. Thank you very much.